So hi everyone, my name is Maxim Andreev. I'm software developer. I write in different languages, and you can find me by handle cdump in GitHub, XCOM, and Telegram. So in today's talk, I'm gonna tell you about control flow graph. I will overview existing tools which can help you deconstruct to get control flow graph from EVM bytecode. Then I will describe the algorithm which I developed to benchmark this tool. After that, I will present you my new unique algorithm which outperforms all existing solutions in terms of speed and accuracy. And finally, I will talk about my open source EVMole library where I implemented these algorithms and some other useful algorithms to analyze EVM bytecode. So let's start. Here is a basic contract source code. It's Solidity. It's like a simple token with only transfer function. And all examples in my presentation will be based on this program, on this contract. So if we compile this with Solidity compiler and ask to output the binary runtime bytecode, this is exactly binary part of runtime bytecode, which is deployed inside the blockchain. So this is what's stored inside blockchain when you interact with the contract. And as you can see, it's just a number of bytes, and let's start to try to analyze it. The first part we can do is just disassemble it, because as we know, EVM is just stack-based virtual machine, and it executes opcodes one by one. And by reading the specification, we know that if we see the bytes like 60, 80, it corresponds to push one 80 operation, and if we see bytecode byte 52, then it's mstore. It's one-to-one mapping. It's all in the EVM specification. Next part, we can define a basic block. This is the definition which I use. The basic block, you can read it here, but in other words, it's the part of the bytecode, part of the contract program, where execution only goes forward. So if you start executing the first opcode of this basic block, then you definitely will execute the last operation of this basic block. Of course, if you are not running out of gas. Using this definition, we can split the previous bytecode to these blocks. Like if we see conditional jump, then it's by definition start of new block. Then we have some instructions, again conditional jump, start of new block. Here we see revert. So again, by definition, we can start a new block and so on. These basic blocks is very common in the program analysis. So it's usually the first time of every analysis based on the bytecode, because these basic blocks by definition are very easy, and the control flow cannot get out of this basic block. If we take a graph of these basic blocks connected of the first program, from the first slide, we can see this one. And if we zoom some part of it, we can see some blocks which we can read. As you can already remember, the first instruction is usually push 180, and on the 11 offset, we have conditional jump, and we can take a false branch or the true branch, and so on. Same thing for the conditional jumps, and we can have non-conditional jump where the destination is on the stack. So here we can have only one edge. Here I mark revert blocks by red, but it's no matter, doesn't matter. So there are some existing tools which can help you build this control flow graph from the bytecode, which is the sum of them: EVRSolve, EVM CVG, as EVM. It's written in Java, Rust, JavaScript or TypeScript, and Python. But what's the problem? Here's the slide from my previous talk at ETHTaipei, where I presented my EVMole library. The talk was about function selectors and arguments from the bytecode. And here we have exactly the same problem. We have some tools, but how accurate are they? Which one is the best? We don't know. Like, we have some tool like black box, and no, it's not black box, it's open source set, but we don't know how accurate are they? So I think it's the first part which we need to solve. So here is my proposed benchmark algorithm. The first one, we need to construct basic blocks by definition from the previous slides. Nothing new here. And after that, we can filter out definitely unreachable block. Because some compilers can generate that code. As you know, in the end of the bytecode, there's some metadata inside the contract. So using this technique, we can find block which is definitely cannot be reached, because in the EVM virtual machine, by definition, you cannot jump to any arbitrary location inside the contract. You can jump only to the destination which opcode is a jump dest. So using this technique, we can do it. After that, we can get definition to the two sets. The first one is the set of all basic blocks after initial partitioning on algorithm from the previous slide. And the second set, we run some tool on the same bytecode and get another set of blocks which is reachable from the start of the contract based on the output of some algorithm. And using these two sets, we can get two useful metrics like false positives and false negatives. The first one is the blocks that algorithm claims reachable, but it's definitely not reachable by our analysis. And the false negatives, it's valid blocks, it's not marked but reachable by the algorithm. But as I said, some compilers, especially older versions of Solidity compiler, or if you run modern version without enough optimization runs, or some older Viper compilers, may include that code. So it's not good, but anyway, I assume that the fewer false negative, if we compare different algorithms, usually indicates more precise analysis. And based on this algorithm, I benchmark every tool I mentioned before and get these results. Here, false positive is 0, which is good, but false negatives dramatically differs. For example, the worst one is EVM CVG builder. It's like 80% of false negatives. And here you can see in the first column is EVMole. This is open source library where I implement the algorithm, which I will describe on the next slides. You can see it's not only outperforms in terms of false negatives, it's 3% of false negatives compared to the second place is 6.3%. But also the execution times is the lowest. It's only 34 seconds. These benchmarks were performed on the largest 1K dataset, which I obtained I download all verified contracts, get top 1K based on the size, and assume that if the size of the contract is the biggest, then probably it's the most difficult one because they have a lot of logic inside and so on. Let's now dig into the algorithm which I implemented. Here this is the three basic blocks, and you can see that in this case we can directly see the jump destination. Here is the conditional jump. For the false branch, we just, it's next instruction, like we have 0b, now we jump to 0c on the false branch. And for the true branch, the jump destination must be on stack for conditional jump, and it's pushed one instruction before. So it's trivial to analyze things like this, and every tool which I checked can solve this without problems, this trivial case. But what if we have some basic block like this? Jump dest, swap, swap, pop, jump. We don't know the jump destination. It's pushed on the stack maybe 10 blocks ago, maybe even in the start of the program. So this analysis is not trivial, and this is the part where my algorithm outperforms existing tools. So let's start with the description. The first part is the stack analysis. As you can know, EVM is a stack-based machine, and every bytecode, every opcode interacts with stack, memory, storage, and here we'll take a look into the stack. I introduce 3 types of stack values, like symbolic stacks, like before n, it's the nth element of the parent stack. So on the input of each block, we can like represent the stack as before 0, before 1, before 2, before 3, and stack grows up. Jump dest, if we find offset to the valid jump dest destination, and the other, it's a result from the other opcode, because every opcode, like it's call opcode or mstore opcode, somehow interacts with stack, but we are not interested in this during this analysis, so we just mark that some element from the stack on the stack. So on the input we have this symbolic stack, we execute basic block and got some another stack state. So here's an example. Here's stack on the input, here's the basic block, and we can execute it extraction by instruction, like swap 2, we just swap 2 values, this one with 0, 1, 2 with 2. So stack looks like this after swap 2, after swap 1 like this, after pop like this, and after jump like this. So here we can see that the jump destination, so it's before 2. So let's perform same analysis for each block, each basic block inside the program. So here basic block and corresponding stack. And now we can collapse some stacks. For example, we have some block inside here, and we know it jumps to before 7. And we want to know to which location it's really jumped. And we know stack states for each parents of this block, and we can collapse this and this to this. No, because we just take other to other before 0 becomes 0. It's a top location of the parent stack before 2, and then we just copy the values of the parent stack. And same thing for this. So this branch can be collapsed to this in terms of the state of stack, like modification of the stack after execution of this block. So here we can see these blocks jumps to some value which is before true, and the parent state of the stack state of the parent is like this. So before 2, 0, 1, 2, so it really jumps to before 1. We see that before 1 is unknown to us, so we need to go up, see the parent of this stack to know the exact location of the jump. So The algorithm looks very simple. We can recursively explore all parent paths until we find jump dest location, repeat until we know all unknown jump destination, and we solve it. So here's implementation of this algorithm. It's in Rust. It's simplified a little, but the main part is we iterate of the parents of the current location, and we analyze the stack state. If it's other, we do nothing. If it's jump dest, we finally find the jump location, and if it's before, then we need to recursively call itself with new path and analyze all parents. Here's the main functions, like resolve this parent, which I described 4 slides earlier before the collapsing of the state of the blocks. Get stack, it's just getting nth element of the stack, and get parents, we have like hash map of all parents of. But we can see cycles, and that's the tricky part, because a node can be visited multiple times, and unlike if you know graph traversal algorithms, usually you use hash set to visit every node only once. But we cannot do it here, because valid path of execution of the contract can visit each node multiple times. So we cannot use this approach. And here I introduce like intermediate states, how I call it. What I use, we have a jump destination which we are looking for. Like we are trying to resolve jump destination for current block. We know which jumps to like before 3, and we know its parent collapsed parent stack. And I said that if we hit this node again and with the same state of the parent and the same stake sim, then we just trying to repeat ourselves, and we can break early this path. So the code before, we need to just modify it, like only proceed this if state jump is unique, like new. And also another precaution, limit the number of operations during analysis for additional safety. Like if for some reason my algorithm is not working, we don't want to spend infinity time, so I limit, like, I don't remember, maybe 500,000 operations or maybe less, but it affects only free contracts of all mainnet contracts. And by the way, all mainnet contracts, it's about 1.5 million, was analyzed in 13 minutes on 24 CPU cores. So this algorithm works very well and failed only in small number of contracts. And of course, sometimes I cannot find the true location of the stack, of the jump. So I not saying that this some random value, just using option of USIDE, so it can be none or null if you prefer JavaScript. And then this is how analysis results looks like. If it's jump, I output the jump destination. If it's conditional jump, I output the true and the false location. And if it's dynamic jump, then the destination of the jump based on the path we took to get into this node. And what makes this algorithm unique? At first, it's a bottom-up traversal, because some algorithms which I reviewed before take another approach and goes from top to bottom. This algorithm avoids path explosion because it significantly reduces the complexity, and it identifies loops without false positive using these intermediate states. And as I said, it's all implemented in EVMole library. It's a Rust and JavaScript and Python library, so you can use it from the language which you prefer. It's open source on github/cdump/evmole. And few words about this library. It has online demo at evmole.xyz. So besides the control flow reconstruction, it can also extract selectors of the contract, the arguments of the function, the state mutability, the storage, like this function reads storage at 0 slot, and the type of this storage is mapping from address to unsigned integer. It also can disassemble, identify basic blocks, and build control graph, which is you can interact with it with your mouse. So it's evmole.xyz, and that's all. This is linked to the library. This is linked to the source code, and this QR is pointing to one of these links. I don't remember which one. Thank you.
Thank you. Now we got some time for questions. Anyone has questions? Yeah.
So how would the EVM object format affect your algorithm? So how would the work on the EVM object format?
It's not supported yet. I took a look into it. It's quite simple as first look to add it, but I postponed it just in case. Maybe it will be released. I will implement it, but it's not the case. Like it's trivial to add.
Thanks for the question. Any other questions? Hey. Sorry.
Some like 300 contracts, 333 contracts that were affected by your limitation on the number of analysis steps. Do you remember if there was any like widely used contract among those, or not? Because
I don't remember exactly, but I took a look at some of these contracts, and some were written in assembly, so it's not output of the compiler, and some I don't know how it's produced. It's very strange contracts. So at first I tried to fix it. Probably it's a bug inside my library, but after I performed the benchmark on the whole mainnet, I found it's only like few hundreds of contracts on the whole network, so it's better just to ignore it. It's fine. Very small number.
One last question. Okay, so that was a deep dive. I think it's the first time I saw so many bytecode in the conference talk. So thanks again to Maxim from EVMole.